Good morning everyone, and today I'll be talking about combining digital aerial survey data and passive acoustic monitoring data. And this was a project that consisted of several of us from CREAM at the University of St Andrews, ScotMER Consulting and HiDef, and was funded by the Scottish Government. So before I dig into the details of the project, I'd really like to acknowledge everybody who helped and supported the project along the way, and that includes the Scottish Government project team, the project steering group, who also provided input, and Paul Thompson and Laura Williamson, who helped us with setting up the data for the case study. So thank you everyone. So the project background. It's important, as we all know, to assess the potential impacts of marine renewables on marine mammals. And absolute abundance, density and distribution data are key sources of information to do that. And so we need to ensure that those estimates and data are as robust as possible. And digital aerial surveys, otherwise known as DAS, and static passive acoustic monitoring PAM surveys are two relatively recently developed survey types compared to the more traditional aerial, visual aerial and ship-based surveys. And as with every different survey platform, there's different strengths and limitations to each. And so with DAS data, just as with visual aerial data, it's possible to collect data over large spatial scales, whereas with static PAM, it's possible to collect data over long temporal scales, but potentially not quite as big a spatial scale as DAS data, given that the PAM instruments are fixed in space. And so the question for this project was, can these two sources of data be integrated to improve robustness of estimates? So the project goals basically broke down into three. The first was a modelling framework to integrate DAS and PAM data, to perform an analysis on a case study specifically for harbour porpoise at a specified site in Scotland, and then to consider recommendations on standards for static PAM and aerial survey data collection to support combining these data sets in an integrated way. The project ran from January last year and finishes this month, and consisted of a series of technical meetings to discuss methods, so what methods were available to us to explore, software, the tools available for us to support our analyses, and finally talking about survey design and potential recommendations. And so we also prepared the data for the case study, which was focusing on harbour porpoise survey data collected from the Moray Firth. And the main deliverables for the project will be the final report and the code accompanying the analysis. So the methods. There are several approaches to integrating data, and we opted for a calibration method where absolute density or abundance is estimated from one survey platform and used to estimate the missing parameters required to estimate absolute abundance or density from the other platform. And this was an approach demonstrated by Jacobson et al. A few years ago. And for our data, we had combined DAS and PAM data from August and September 2010 collected in the Moray Firth, and the figure shows an example of a series of transect lines from one day of DAS data collection. So our workflow was as follows. After establishing the project goals, which was to integrate the data, we had the PAM and the DAS workflows, each with their own survey design considerations. And then the data collection differed in that, as discussed, DAS was collected less frequently, so we actually had 4 survey days over 2 months, and the PAM instruments were collecting data continuously. We performed absolute density estimation and spatial modelling on the DAS data and fed that into a Bayesian model in R to predict the missing parameters required to estimate absolute density from the PAM data. So that led to our result, which was absolute density estimates at each PAM station through time, including time when we had no DAS data. So here are some of our results. So on the y-axis is density with animals per square kilometre, and on the x-axis is date, stretching for the 2 months that we had data for. The first 3 points, however, in blue are estimates from using the DAS data only. The first is a design-based estimate, and the second 2 are from a spatial modelling exercise. And then the rest of the time series are density estimates using the PAM data with the missing parameters that we've derived by using our DAS data. And everything has associated uncertainty. And so we can see that by using the DAS data, we've been able to convert that time series from the PAM data into absolute density estimates. So our conclusions. We successfully managed to integrate PAM and DAS data with associated uncertainty, and we were able to enhance the benefit of that continuous PAM monitoring by turning those data into absolute density estimates. The next steps are that we'd like to compare different integration methods because how we integrate different data sources is an area of active research. And we'd also like to consider more of the integrated survey design considerations, including downsampling the PAM instruments. We actually had 43 instruments available for analysis, and we'd like to see what happens to our parameter estimates when we don't have as many. And impact. So this could impact future recommendations, certainly regarding survey design and data collection, which could ultimately impact required survey effort and ultimately cost. So that's an overview of our project. Thank you very much.
Hello, my name is Jessica Motabaranom and I work as a research assistant here at the Sea Mammal Research Unit. I'm going to be talking to you briefly today about seals on sonar, their abundance and distribution around an operational tidal turbine. And this has been very much a team effort and there's my co-authors that are listed just below here. So tidally energetic environments are of great importance to the tidal energy industry, but to a number of marine mammal species as well. However, up until recently, there's been a real lack of data and knowledge on the behavioural responses of marine mammals to these tidal turbines. And this has led to some concerns. Because of the nature of the rotating blades of the turbine, there is potential for fatal collision between the rotating blades and the seals, and in some parts of Scotland the harbour seal population has been in decline for quite some time, and so it's really important to gather more data and information to address these concerns. So there have been a few other studies on marine mammal behavioural responses to turbines, and these include harbour porpoises that demonstrated fine-scale avoidance of the rotating blades, so this is within the tens of metres, and using telemetry we were able to demonstrate large-scale seal avoidance, so between the hundreds to thousands of metres. However, in order to fully understand and assess collision risk, we really need more fine-scale seal data, which up until now we didn't have. One of the reasons behind this lack of data is because of the technological challenge of tracking seals underwater at the kinds of spatial temporal resolutions that we required. So in order to do this, we used our marine mammal hiccup, which is our seabed platform that you can see here, and this consists of two multi-beam imaging sonars that work at a 720 kHz frequency. And so the reason that we have two is that it allows us to cover the whole water column. So we have one that points towards the sea surface at a 30-degree angle and the other one which is parallel to the seabed. As well as the sonars, we also have a small array of hydrophones that allows us to differentiate between different vocalizing species that might be detected. And so the way that this platform was designed was that it would receive power directly from the turbine through an umbilical cable, and then it uses fibres in the export cable to relay back data in real time to a shore-based computer. And the rationale behind this was that it would allow us to collect many months of data and a sufficient number of encounters between seals and the turbines. Once we have the raw sonar data, we run it through PAMGuard, which is our bespoke movement detector. And essentially, PAMGuard is an interface that allows us to quickly review, identify and classify targets of interest, as well as providing it with a nominal confidence score, with 1 being the lowest and 5 being the highest. And so at the moment we are manually reviewing the tracks, and we feel like this is a conservative approach to have because we don't want to miss any potential targets of interest before moving towards a fully automated system in the future. So as you can see here, where the blue arrow has just popped up on the left hand panel, that is actually pointing towards 2 seals, and on the right hand side you can see a blue and pink track, which is what PAMGuard has detected as targets of interest. But if you're interested in finding out more, we did publish a paper, a methodology paper on this a few months ago. It's just popped up here, and you can scan the QR code and it will take you to that paper. So this is actually the example video from the previous still, with the 2 seals that are popping up in the left-hand sonar, which is the upper sonar. So you can see them moving across, and as time goes on, they gradually start appearing on the right-hand sonar, which is the sonar pointing towards the seabed, which indicates that they're moving down the water column. We've also actually detected a number of other animals on the sonar, not just seals, but a number of sharks, skates, fish schools, and diving birds as well, which has been really interesting from an ecological perspective, but has made identifying seals slightly more tricky. But at the moment, we have audited 380 days of data, and this equates to almost 17,000 megafauna tracks that have been manually reviewed. So we have 709 three-dimensional seal tracks with a confidence score of 2 or above, and the highest rate was detected throughout the winter, in January to be precise, where we had almost 5 seals a day. So this is to be expected because of our site's proximity to breeding and pupping grey seal sites. So for some more preliminary results, you'll see on these plots are all of the seal tracks across the year and across all the tidal states. And so the blue dots are the start of the seal track and the yellow dots are the ends. So you'll see, depending on what tidal state is in, they'll be flowing in certain directions or hanging around the turbine more, with the turbine being the yellow and grey structure in the middle of each plot. We haven't done any statistical analysis on this yet. This is ongoing, so we will keep you updated with those results in the months to come. Some more preliminary results on seal tracks and behaviour next to the turbine. So there are some seals that just appear to drift along with the current. So as you can see in this plot here, the blue dots are still the start of the track, the yellow dots are the end of the track, and the red arrow is the direction of the flow, and any given particle that will have started at the beginning of the track, its direction of flow and the distance it will have travelled if it were just drifting. So as you can see, that seal pretty much is just drifting. However, there are some seals that are showing avoidance, like on this plot here, and we have 60 tracks where the seals seem to approach the blades within 2 meters. So these tracks are currently undergoing final analysis. So we are currently quantifying seal avoidance, so that this will allow us to investigate the implications of seal avoidance on collision risk and feed this into collision risk models in order to further support the tidal energy industry. And we're also planning on investigating the influence of environmental covariates on distribution, as well as moving towards a fully automated classification system. And lastly, I'd like to thank all of our funders and collaborators that are listed here. And if you'd like to get in touch or just to have a look at what our research group is doing, you can scan the QR code. So thank you for listening.
Good morning, my name is Michael Wood and I am an underwater acoustic modeller for JASCO Applied Sciences. JASCO are a worldwide company that cover all aspects of underwater acoustics, including regulatory advice, field recordings, data analysis and modelling. In the presentation today, I'll be going over a method of predicting the noise generated from marine piling that is based on using energy conversion factors. In the presentation today, I'd like to run through a bit of the background and how we got involved. We'll also have a brief look at the energy conversion factor, or ECF method itself, and how it worked. We then split the method and have a closer look at how the source is defined and how the sound is propagated. Following this, we'll cover some potential issues and wrap up with some of the recommendations. So in the construction of offshore wind farms, impact piling is a common method used to install monopiles that serve as the foundation for the wind turbines. The construction involves the hammering of very large piles into the seabed, which generates a huge amount of noise that can propagate substantial distances. This of course has an effect on marine life, and so it's important that we're able to predict how far the sound travels. For this we use underwater acoustic propagation modelling. Now there are numerous approaches and models used, but one that has been popular recently is that of using energy conversion factors. It is a simple approach that looks very attractive in its simplicity, but it is not well understood. Because of that, and given its increased usage, Marine Scotland approached us to help them better understand the method and to provide recommendations as to its usage in the future. So, looking at the ECF method, it is a simple way to calculate a source level that can be used in underwater sound propagation modelling. Broadly, the method has these 3 steps. First is to calculate a single broadband value for the source level, for which the only variables are the hammer energy and the ECF itself. C and ρ here are the speed of sound and density of the water respectively. Second, one can calculate the spectra by using a recorded pile spectrum and shifting it in level to achieve the same broadband level calculated in the first step. Finally, the frequency-dependent source function is used in propagation models to generate the full sound field. So at face value, the ECF method looks straightforward and sensible. There are, however, a couple of sticking points. In the derivation of the equation on which the source level calculation is based, it is presumed that there exists a region in the sound field where sound radiates spherically, as if it all radiated from a single point. The derivation also inherently presumes that the source exists in just a single medium. Historically, when the sound fields from impacted piles were first modelled, no one knew better than to model it as a point source. Research later showed, however, that the pile should be a line source rather than a point, and consequently the stated formula is not appropriate for piles. It should also be noted that there are only a handful of estimates of recorded ECFs in the literature, and across this handful the range of values is wide, between 0.17 and 1.56%. I'd now like to look a bit closer at the sound propagation. In the vast majority of sound propagation models, one models the sound as if it propagates from a single point. This is agreed to be valid for the majority of sound sources that we encounter. In the case of propagation from a point source, there are typically 3 regimes of propagation. Close to the source, the sound radiates in spherical shells. The wavefronts then get to a point where the energy is effectively trapped between the water surface and the seabed and spreads in cylindrical shells. Then further away, we see energy travelling at angles further away from the horizontal lose more energy, which gives us what's called a mode stripping region. There are of course differences for different frequencies, but this is essentially the general pattern. I think it's instructive at this point to see the modelled sound field from an impacted pile. This is the radial slice through the water with the pile on the left-hand edge. The horizontal black line represents the seabed, and what we'll see is the progression of the pulse from the hammer travelling down the pile, generating a conical wavefront that propagates in the water. The stress wave is reflected at the pile toe, and thus we get the opposite wave on the way up. So as we saw from the graphic, the propagation from piling is different. There is no initial spherical spreading, so skip that entirely. And as the energy essentially travels at one fixed angle, there is no mode stripping region. What we see is the wavefront at a specific angle trapped between 2 boundaries, losing energy with each bounce. Rather than the point source model, we can better describe this using a damped cylindrical model. Based on this, the propagation follows a cylindrical spreading or 10 log R term plus a damping term where energy is lost to the sediment with each bounce. So why is this important and how much difference does it make? Well, in fact, the combination of the source level prediction and the incorrect propagation can lead to very large errors. This is one example from a benchmarked piling study, and it shows the modelled sound level as a function of distance from the pile for a dedicated pile noise model and the ECF method with point source propagation. As you can see, there are large underestimations of the sound level within the first 5 kilometers of around 10 dB. However, at greater distances, around 10 kilometer mark, as you can see from the slopes of the curve, the point source model overestimates the sound levels. This of course will have an impact in determining how many marine animals are affected by noise, as guidelines are typically based on exposure to given sound levels. So the bottom line of this presentation is that we recommend that this approach is not used to model the sound generated by piling. As shown, given the assumptions inherent in the process, it is inaccurate for piling and has been superseded by more modern approaches. The alternatives, well, it depends a bit on how much detail you already have. If you happen to have made recordings and retrospectively want to determine what the likely levels were, then the damp cylindrical model is ideal within the first 5 kilometers. If you require predictions of a new situation that is very similar to one that you already have results for, then there are methods that you can use to scale the results based on basic changes in the pile, the hammer, and the environment. In most cases, however, sound level predictions require more specialized methods, typically using numerical modeling. Here, the important factors are that the source function represents the distinctive wavefront of the pile, and that it is used in an acoustic propagation model that supports the wavefront of this nature. So that's all from me. I hope you found the presentation interesting, and I look forward to questions a bit later. Thank you.
Good morning. My name is Nienke van Geel, and on behalf of my co-authors, I'm presenting the results of the Fortune project, which aimed to characterize the underwater noise of 2 types of floating offshore wind turbines currently operational in the UK. Many countries have set marine renewable energy targets. Offshore wind is a rapidly developing industry and has become a priority for many countries seeking to meet their goal to reduce greenhouse gas emissions. Floating offshore wind is expected to add significant additional energy generation capacity soon, capitalizing on resources available in areas with larger water depth. Offshore environments are habitat for marine mammals and increasingly of interest for offshore industries, including marine renewables and specifically floating offshore wind. When it comes to underwater noise from floating offshore wind, we need to understand operational noise levels of different turbine designs and of different turbine sizes. For fixed wind, we know that turbine design and size will influence the type of noise and the noise levels produced. This can influence behavioral responses and potential auditory injury to marine mammals, which will also depend on species sensitivities at different frequencies. Noise levels and potential impacts are also dependent on floating offshore wind array sizes, as has been shown for fixed offshore wind. Systematic measurements of underwater noise generated by floating offshore wind turbines are currently lacking. The lack of such empirical data impedes noise impact assessments and is increasingly being discussed as a potential consenting issue. To address this knowledge gap, the Fortune project aimed to describe baseline noise characteristics and noise levels of floating offshore wind turbines deployed on 2 different foundation types. Acoustic data were collected at 2 wind farms on the east coast of Scotland. One is the Kincardine wind farm of Aberdeen, which consists of 5 9.5 megawatt turbines deployed on semi-submersible platforms and is operated by Principal Power. The second site is the Highland Scotland site of Peterhead, run by Equinor, which consists of 5 6 megawatt turbines deployed on spar buoy platforms. At each site, recordings were taken at various distances from an individual turbine for about 1 month to capture different weather conditions for describing baseline acoustic signals and noise levels. These data were then used to back calculate source levels of devices and model footprints of radiated noise of turbine arrays to assess the potential for turbine noise to cause injury or impact behavior of marine mammals. 2 turbine-related noise sources were identified. The first is noise associated with the operation of the turbine, such as from the generator and rotating blade. The second noise is mooring-related noise, which is typically seen as infrequent broadband noise of short duration. Here, the top right spectrogram presents time on the x-axis and frequency on the y-axis, with the intensity of sound for each time-frequency combination indicated by the color scale. At Kincardine, operational noise revealed distinct tonal sounds between approximately 30 and 120 Hz, with most energy concentrated between 50 and 80 Hz. After exclusion of mooring-related signals, the 1/3 octave band levels were matched with environmental time series, including wind speed, wave height, and current velocity. The bottom plot presents the correlation between noise levels measured at 600 meters from the turbines and the environmental conditions for selected frequency bands. A positive linear correlation with wind speed was revealed for most frequency bands. At Hywind Scotland, the wind farm with the Sparboy design, two dominant tones at 25 and 75 Hz were found in many of the recordings. For both wind farms, tonal features were visible at frequencies up to 350 Hz, although these were much less dominant at these higher frequencies. At Hywind Scotland, a positive relationship was present between the noise level measured at 600 meters and wind speed, as well as with wave height for most frequency bands. Array-sized noise fields were modeled for a range of different scenarios. In general, the combined noise of the multiple operational turbines resulted in a smaller acoustic footprint for Hywind Scotland than for Kincardine, as exemplified here by the unweighted close-range acoustic footprint at 19-meter water depth for Hywind Scotland on the left and Kincardine on the right. Using the 100 decibel contour to approximate median ambient noise levels in many parts of the North Sea, the predicted noise field showed that unweighted sound pressure levels for the 5 turbine array scenarios were above ambient for maximum distances of 3 to 3.7 km from the centroid of the array at Hywind and 3.5 to 4 km at Kincardine when assuming 50 meter per second wind speed. Low frequency turbine noise was accompanied by transient sounds which were clearly related to the mooring structures of the turbines. An increase in these broadband transient signals was found at both wind farms during periods of higher wind speeds and significant wave height. These impulses were generally of short duration, typically 1 second or less, but were produced in sequences often lasting for prolonged periods. Overall, the frequency of occurrences of these transients was variable at both sides, but considerably higher at Kincardine compared to Hywind Scotland. The presence of these transients appears the biggest difference between operational noise of fixed wind and floating wind turbines. Higher frequency of transients is important to consider in relation to environmental impact, as the presence of transients, and especially the intermittent presence of the signal, could impact and trigger behavioral responses of marine mammals that are different from responses to continuous turbine sound. When looking at harbour porpoise presence from click detectors deployed at 3 to 600 meters from the turbines to those deployed at distances of over 1500 meters, the initial results indicate, for both sides, a reduction in porpoise click detection closer to the turbine as compared to further away. Additionally, the number of daily detections were higher at Kincardine compared to Hywind Scotland. This is likely an effect of change in seasonal presence, as reported by other studies undertaken in the region. Work on the subject is ongoing by Danielle Harris, a PhD student at the Environmental Research Institute and co-supervised at SAMS. The final project report is available via the link provided here. With this, we would like to thank SuperGen for funding this project and our collaborators at Equinor and Principal Power for their support and site access. We also thank First Marine for their help in deploying and retrieving the acoustic moorings, as well as the project steering group members.